Molecular and ionic compounds. Alright, so we're doing really well. We understand, or we're beginning to understand atoms and how they're made out of, the fact that we can combine them together. We have elements, we have compounds, all that type of stuff. Alright, atoms, we already know the number of protons will determine the atomic identity. The number of neutrons, you change that, you get different isotopes of any one particular element or atom, and you change the number of electrons, you get an ion, right? The charge, either positive or negative. Well, why do some like to be positive and why would some like to be negative, or can they all be different? Now, there are actual charges that these atoms are stable with, and whereas a sodium perhaps might be stable with a positive 1, a calcium is not, whereas a calcium is stable with 2 positives. Fluorines are stable with a 1 negative. And so why is that? Why are some positive, negative, and why the difference? And it all goes back to, and you look at a periodic table here, the noble gases. The noble gases are the last column right there. Okay? And there's something particularly stable about the number of electrons that the noble gases have. And when we get into atomic structure, we'll understand just why. But for right now, recognize that the noble gases are very stable. They have the right number of electrons, and other atoms out here, other elements I should say, could become more stable if they adopted the same number of electrons that those noble gases do. Okay, so that's what I have down here as an example. Fluorine. Let's take a look at fluorine. If I call up a periodic table, fluorine is right there. It's number 9, so it has 9 protons, and in a neutral fluorine atom, it's going to have 9 electrons. All right. Here's the last column of noble gases. Neon is number 10. So neon has 10 protons and 10 electrons. Fluorine is only 1 away. Right? If fluorine gained 1 electron, it would be like neon as far as the number of electrons, and that would be a stable arrangement. So that's what fluorine likes to do. It's 9 electrons. We like to add an electron to it. It gives an F-. Now it's the same as neon. Sodium. Call up another table here. Sodium, way over here, it has 11. So 11 protons, 11 electrons. If it loses one of those electrons, then it'll be like neon with 10, and that should be a stable arrangement. So that's what sodium likes to do. It actually gives off an electron and becomes positive. So very often, it's not a perfect rule, but very often they like to be like those noble gases and gain electrons or lose electrons to be like it. One last example here, sulfur. Sulfur is right down here in the oxygen column, 16. Argon has 18. Pretty obvious, if it gains 2 electrons, it will be stable. All right. Here in your book is a figure showing common charges of these. Not surprising that any one of these in the first column, if they lose 1 electron, they're going to be like these noble gases. So all of these like to be a +1 charge. In the second column, +2. These over here in column 17 like to gain 1 electron, and so F-, Cl-, Br-, they have a 1- charge. Oxygen, sulfur, 1 or 2-, excuse me. These guys like to be a 3-. Usually ±3 is about the limit, especially for small atoms, that you'll see. Putting more than that on one is often unstable. Carbon sometimes shows up in what appears to be like a 4- charge. Fairly rare, kind of a special chemistry, special bonding for that. So usually ±3 is your limit, but again, those are not hard, fast, concrete rules. We can break them. Look at the transition metals here. The transition metals are unique in that they often will adopt multiple charges which are stable. Well, that's because if you think about this, here, iron right in the middle, it would have to lose a bunch of electrons, or it would have to gain a bunch of electrons to become like a noble gas, and that doesn't happen. So we're going to look at, after we understand atomic structure, we'll see why +2 and +3 for iron are both stable. There are good reasons for that. We don't have that understanding quite yet, though. All right. So this chart is useful for understanding common charges for these transition ones. Platinum 2+, gold +1 or +3. Mercury +2 or +1 actually comes as a dimer, right? Chromium +2 or +3 as well. Once in a while, you'll get ones that are actually not in the transitions couple of these out here, like tin could be +2 or +4 as well, and we'll talk about that later. All right, polyatomic ions. These are groups, compounds if you will, which also pick up an extra electron or give off an extra electron like that. And so the whole group, the whole compound if you will, becomes an ion. They stick together, they stay together, but they have a charge. We call them polyatomic ions. Here's a table, 2.5 from your text, that lists all the common ones. Don't worry about this last column yet, just look at these first two columns. The only two positive ones are NH4 plus, ammonium, and H3O plus, which is hydronium. However, we got a lot of negatives, lots and lots of negatives here. O2 minus oxide, O2 2 minus, so two oxygens stuck together, but again carrying a whole extra 2 electrons, so the whole thing has 2 minus charge per oxide, and so forth and so on, right down here. These are extremely important to get down. You do need to memorize the names of these and their formulas. Their formulas would include how many of each atom and what the charge is. There are some patterns, and I'll point those out to you, make it a little easier to memorize, but make yourself up some flashcards, get these things memorized. You need to know them. What are some of these perhaps trends that will help you to memorize it? Well, for example, if I look down here, here is carbonate, CO3 2 minus, and then bicarbonate, HCO3 2 minus. That bi on the front does not mean 2. It's actually an older terminology that we're stuck with. It just means there's a hydrogen on there as well. Hydrogen, remember being in group 1, that first one, it likes to be a +1, so I think it makes sense if I take a carbonate with a 2 minus and add a positive hydrogen, now it's only a 1 minus on its charge. So things like that, that's a little bit of a trend for you, you'll see that. Other ones do the same thing, except we don't call them bi usually, we just call them hydrogen. That's even simpler. So here, sulfate, SO4 2 minus. If I put a hydrogen on it, now I got HSO4 1 minus. So again, that same trend with the charge. This is called sulfate, this one's called hydrogen sulfate. All right. Here's sulfite, SO3 2 minus, hydrogen sulfite. All right. Phosphate, hydrogen phosphate. This actually goes to 2 hydrogens, so we call it dihydrogen phosphate. And notice the charge again goes up by 1 towards the positive, that is, each time you add a hydrogen. So that makes sense. Another trend, sometimes there are these different number of oxygens. We've already seen that. And so, for example, look at the nitrate and nitrite. NO3 minus 1 is nitrate. NO2 minus 1 is nitrite. 8 versus 8, that one vowel difference is the only thing that's different with the names. But it's a trend there that will carry on. So look at sulfate, SO4 2 minus, sulfite, SO3 2 minus. Obviously, the one with the more oxygens has the 8 ending. The ones with the less oxygens has the ite ending. Right? They have phosphate, PO4 3 minus. They don't have it on this table, but there is a phosphite, and it's PO3 3 minus. Okay, and so here's chlorate and chlorite. You have bromate and bromite as well. Iodate and iodite. Right? Those same trends. Right? With the chlorates, the halogens in general, bromine, iodine, those guys, you actually can go higher and lower, and there are additional options, higher and lower in the number of oxygens, that is. So the higher one, chlorate, ClO3, chlorite, ClO2. And can I go even lower? Can I go just ClO? Yeah, you can. With the chlorines, that does show up. And so they say instead of chlorite, it's hypochlorite, which makes sense, the hypo meaning below. And so relative number of oxygens again. Here's chlorate, ClO3. Can we go above it? Turns out you can, and so ClO4 is perchlorate, that per being short for hyper meaning above, and so again the number of oxygens are what we're talking about here. Now again, the chlorate and the chlorites, they also work with the bromates and the bromite, iodate, iodite. They're not listed here specifically on this table, but you can do that as well. Alright. The types of bonds then that I can form to make these molecules either use these ions, which could be single atoms, or these polyatomic ones that we just talked about, or they can use what's called covalent bonds. Right? Ionic bonds, like the ones, or using the ions like the ones that we just talked about, are made by transferring electrons. If I actually add an extra electron or remove an extra electron to form that charge. So electrons are transferred, ions are formed, and once I do that, then I can create what's called an ionic bond. We'll talk about that here in detail down below. Covalent, on the other hand, electrons are shared, so we're not making ions over here. We're not actually transferring electrons or adding extras. All right, we're going to be sharing them. That's kind of have a special set of rules. All right, but ions are not involved. All right, so let's talk about the detail here of ionic compounds. Ionic compounds form ionic bonds, or made of ionic bonds, I should say. Different categories. If you're talking about single atoms, not the polyatomic, but just the single atoms, it's often between a metal and a nonmetal. We saw up above the position of metals and nonmetals in the periodic table. And so if you've got one that's way on the left side connected to something that's way on the right side of the periodic table, that's going to be a metal and a nonmetal. And 99.9% of the time, that's going to be an ionic bond. It's going to create an ionic compound. So sodium chloride, let's use that as a simple example. Sodium on a periodic table is way over here, definitely in the metal section. Chlorine is way over here, definitely in the nonmetal section. So here's a perfect example of what we're talking about. Sodium chloride is going to form an ionic bond. Right? Why? Well, let's see. Sodium, we know, already saw, likes to be a +1 charge. It wants to be like a noble gas. Chlorine likes to be a -1 charge. Again, likes to be like a noble gas. So this is perfect. I can take an electron off of my sodium, give it to the chlorine. Now each one of them is more like a noble gas, makes them more stable, but they're charged now. They're ions, right? That's a positive ion, that's a negative ion. Well, the opposites in charges attract, and so they come together to form sodium chloride. One sodium, one chlorine, they stick together. Makes perfect sense. So the motivation here is to become like a noble gas. That creates the ions, and them sticking together afterwards is almost like an afterthought. They stick together because they're oppositely charged. Here's another example of an ionic compound, calcium and oxygen. Again, on a periodic table, calcium is way over here on the left. It's in the second one, so I know it's going to have a +2 charge. Oxygen, way over here on the right, nonmetal, likes to have a -2 charge. Same idea then. Calcium will go to calcium +2, where oxygen will become 2-. That's because we transfer 2 electrons over, and we get the new ionic compound, calcium oxide. What about K2O? That's potassium and oxygen. Periodic table, we already saw oxygen's over here, likes to be a 2-. Potassium is in the first group, actually, so it likes to be a +1. Right? 2- +1. That's a little differently. They don't quite match in the charges, but that's okay. We just take 2 of the potassiums. So here, this one gives off an electron to become a +1. A second potassium does the same thing. They both give their electron over to an oxygen, so it picks up 2, it becomes 2-. Now all 3 of them are going to be like a noble gas as far as the number of electrons. They're charged, and so the positives and the negatives attract, and you get potassium oxide here, K2O. So you see that there are 2 potassiums, and it's because of the charges that they like to make, trying to become like a noble gas. You should be able to go back and forth between these. So given the elements, predict the compound and the number, the relative of each one, or you should be able to go backwards here and given the compound and see the elements that they came from. Alright, the polyatomics work exactly the same idea. We're going to have the charges, the positive and the negative, and they're going to stick together. And they're going to stick together so that the overall charge is 0. The overall charge is neutral. So sodium likes to be a +1. From that table here, NO3-, that was one of the one that you memorized. It's nitrate. Alright, +1, -1, those guys are going to like to stick together. Right? Within the nitrate ion, polyatomic ion, is actually covalent bonds, and we need to still talk about that. Right? But between the sodium and the whole nitrate ion, that's an ionic bond. They stick together because of the charges. Okay. Another example here, sodium and one of the polyatomics, sulfate. Now sulfate is a 2-, where sodium is only a 1+. And so I'm going to need 2 of the sodiums, and there's my new ionic compound, sodium sulfate, 2 sodiums and 1 sulfate polyatomic ion. That's why it's very important to memorize the number of charges on these polyatomics as well. If you don't memorize that, there's no way you can do this method. Magnesium and chlorite, Mg2+, well, this is Cl2, 1 minus. Looks like I'm going to need 2 of these. And so there I bring it together. 1 magnesium, 2 of the chlorides. Notice that because chloride has several atoms, then I want to indicate that I'm taking 2 of this whole clump, this whole cluster that I call chloride. And so I put that in parentheses. I want 2 of that whole thing. We don't have to do that for single atoms, but for these polyatomics, yeah, you have to indicate it's the whole thing that I need 2 of. So that's the right way to write that formula. Last example, ammonium from the polyatomics, and here's phosphate from the polyatomics. So 1 plus and a 3 minus. All right, I'll need 3 of those, I guess. Put them together like that. Okay. Now, when ionic compounds form, they don't make molecules. That's important to realize. Ionic compounds are a bunch of positives and negatives, and they stick together because of the charges. Okay? And so what they actually end up doing is forming a crystal, extended crystal type structure. Here's a picture of sodium chloride, where we've got the green chlorides, the positive purple sodiums, and so they're just alternating back and forth, positive, negative, all the way across in 3 dimensions, top, bottom, forward, and back, and they form this whole network of positive negatives that are alternating. So that's what a structure of a salt crystal, sodium chloride, would actually look like. You can see it might be a little more complicated if you've got like a 2-to-1 ratio, but nevertheless it's the same principle that will form. Alright, so going back up here, remember we said there are 2 types. We've got the ionic ones where we have ions and they stick together, and then this covalent, the idea that some of them actually share electrons instead. And so scrolling down here, the covalent, generally called molecular compounds, because they're made out of covalent bonds which do not involve ions. Now, whereas the ionic ones were typically a metal and a nonmetal, so something from the far left and something from the far right of the periodic table coming together, molecular compounds are typically made between 2 nonmetals. So way over there on the right side of the periodic table only, between 2 nonmetals. So for example, water, pull up periodic table. Hydrogen, many times I said, remember, it actually belongs over here right next to helium as well, because it has properties of both. In that sense, I mean, we don't really think of gas helium. That's not really a metal. I mean, metals are solids and they conduct electricity and all that. They're shiny. In that sense, it's easy to recognize that hydrogen belongs over there. Anyway, hydrogen's over here. Oxygen's also over here. Right? I've got 2 nonmetals. Right? They would come together to form water, H2O. Right? Those are going to be covalent bonds. They are going to be, again, non-ionic in nature. Okay. Another example, SO3, sulfur and oxygen. Both of those are from the nonmetal section over here, right on top of each other, actually, right? Sulfur and oxygen. And so they actually come together as an SO3. Here's glucose, C6H12O6. Right? Everything over there is on the nonmetal part, and they're going to make a bunch of covalent bonds making this molecule. Now, why is it SO3 exactly, and how are they connected, and how are they actually shared? We're going to have to wait a chapter 2 to explain that, because we need to understand the structure of these atoms a little bit better. Okay. Right now, you need to be able to recognize that, hey, there's not ions formed, there's not ions involved, and therefore it must be a molecular compound, not an ionic one. All right. Last little point here, some are difficult to classify. When we were talking about the metalloids before, we mentioned aluminum. Aluminum, sitting right here, right on this dividing line between the metals and the nonmetals, right next to the metalloids here, boron and silicon and such. Aluminum is not too surprising that it might have just a little bit of non-metal character. Probably has a little bit of both. You might even want to classify it as a metalloid. I've seen some textbooks actually do that. And so here's a compound, AlCl3. We can understand that as far as bonding and such as being ionic in nature. Chlorines like to be a -1. Aluminum is a 13. If it loses 3 electrons, it would be like neon, which would be plus 10 and make it a +3. And so I can see this where this is like a +3 on the aluminum. I got 3 -1s. It makes good sense, ionic. But when you actually look at the properties of aluminum chloride and of the bonds, there's a lot of actually molecular properties as well. Don't need to get into the details of that. Just put that as an example, as the fact that it's not a black or white sort of thing. There's a lot of gray areas involved here too, and there's a great example of where it looks ionic at first, but it turns out to have strong non-ionic or covalent character as well.